All right, our last lesson for this unit, but we got one more question to finish in the one before it. This question is actually of the exact same variety that was on your test, so I'm already fairly confident you can solve it. It is a bit harder because the numbers are a bit bigger, and it does have it's the cost, not the speed variety of them. So it is going to be the multiplication one. I'm going to go over that really quickly, how to set it up, because I think you did end up getting that wrong on the quiz, on the test, even though it wasn't marked wrong. So we have two subdivisions located on opposite sides of a creek. I'll actually start from scratch. So we have some kind of a creek, and we know that the creek is going to be 100 meters wide. So we have our first point, we'll say is down there. We're going to call P. The company has to connect points P to point Q. Point Q is on the north bank, the top bank, 1,200 meters east of it. So we can pick some kind of point Q, and this is 1,200 meters across that way. And now we have to lay a cable in the most cost-efficient possible way to cross this gap. And it's going to be some kind of a diagonal and some kind of a straight across, assuming it's cheaper to lay it across land. So $40 on land and $80 on water. Yeah, otherwise you want to go straight across water. But if it's cheaper on land, then you want to run some kind of a diagonal and across. So we're actually going to end up with two different sections to this thing, just like before. This guy and this guy. One thing that you did on your test, it wasn't wrong, but it made everything a bit more difficult. Always call x the part in the Pythagorean relationship, and that'll make your equations a little bit simpler. So I'm going to call this distance x, and I'm going to call this distance 1,200 minus x. Okay? Which should bring us to our first formula. The total distance that we're traveling is going to be the distance of this guy right here, this blue water length, which is going to be the square root of 100 squared plus x squared. Makes sense. And then you have to add it to whatever land length is left, which is 1,200 minus x. Okay, so that's just the distance. Now we need the actual cost of this. So we need to turn it into an actual price function. So the cost of it is going to be just each distance times its cost per meter. So this is the amount in the water, so it should be that times 80. And this is the amount on land, so it should be 40, because it's 40 meters on land, times the entire thing. And you need brackets at this point. That's it. So now we know how much the cost is, and you could graph this, and you could actually look for when it's a minimum. But we can solve it algebraically by finding when the derivative is equal to 0, or finding all of our critical points is what we say now. So we need to calculate the derivative, which is going to be a bit annoying. And let's start doing that. Do I have that down here? So of this guy, it's actually just going to be 40 times -1. So it's actually going to be, wait, is that right? -40. Did I have the wrong number there before? Sorry, let me just look at my notes. Yeah, I think that's right. I think I did it a little bit different than, yeah, I did. So that's just a number, and that's -40x. So -40 over there. And then over here, you need to find the derivative of this whole guy. And it should be, if I can think about this. Why don't we actually calculate it? So 80 times 100 squared plus x squared all to the power of half. So the half comes down and it becomes negative a half. So it's going to be 40. And this thing comes to the bottom with a negative a half. So it's going to be a root on the bottom. 100 squared plus x squared. And then times the derivative of the inside, which is going to be 2x. Should look something like that, if I did that correctly. Derivative of the outside, negative a half, times the derivative of the inside, which is just 2x. I think that's right. And then we want to solve that for when that's equal to 0. So we add the 40 to the other side. 40 is equal to, let's say, 80x all over root of 100 squared plus x squared. We can move that guy up. So 40 times root of 100 squared plus x squared is equal to 80x. We can divide by 40. Root 100 plus x squared is equal to 2x. We can square both sides. 100 plus x squared, 100 squared plus x squared is equal to 4x squared. And then we're trying to solve this. Did I do this correct? This seems too easy. Well, let's find out when we finish. 3x squared is equal to 10,000. Divide by 3 and square root. I think I might have done something wrong, but let's find out. I get x is equal to plus and minus, not root, of 57.74 roughly. Which means that this is going to be 57.74 and this is going to be 1200 minus 57.74. Which would make this land distance equal to 1,142.26. 1,142. Boom, did it actually. I actually was doing this before and I defined my x's the other way around and it became like a much, much harder question. This actually isn't too bad. So we found out the land distance is going to equal, actually we don't even know this, we just know this is a critical point. We kind of glazed over that last unit, now we can actually definitely do it. And there's also another one at negative, but that one's going to be outside our domain, obviously. We're not going to have an x value going the other way, so this guy is extraneous. Sometimes we write that x equals negative 57.74. Either write extraneous or not in domain. Not in domain. So we only have the one critical point. Was there any restriction on our original function way back here when we got to the derivative? If there's a restriction, then there's another critical point that we need to check as well. But in these cases, there isn't going to be a restriction, and we can kind of see it. So is the bottom ever going to be 0? It's never allowed to equal 0. So when it equals 0, that means 100 squared has to equal negative 100 squared has to equal x squared, but these are both positive numbers, so you can never actually get to 0. You're never going to get negative 100 squared out of an x squared. So there is no restriction on the domain. Pythag in the bottom is always okay because it's always a positive number. So there's no critical points from a restriction on the domain. There is one critical point on our function, but there's actually two other points we need to check. Or we need to common sense it by graphing the derivative and finding out what kind of a function it is. If you can tell it's going to be a parabola in a certain way, then you might be able to tell it. we could actually do a couple different things. We could do the first derivative test, but I think in this case, it's probably easiest just to do finding what we did when we wanted to find the absolute maximum or minimum on a closed interval. So our interval for x is somewhere between 0 and 1200. So x has to be between 0 and 1200. So we could actually just check all three numbers and find out when the cost is the least. So we have our actual cost function way up here, and we would want to find out the cost of 0, the cost of 1142.26, and find out what the cost of 1200 is going to be. You could do all those things. Is there another way? You could do... Yeah, you could do the first derivative test as well. And in fact, that might be easier than plugging all these numbers. This isn't bad. This isn't going to be too hard. It's just a calculator question. You could also do the first derivative test with intervals. So you could kind of set up your chart. And you could say, I want to check between 0 and 1142. And check between 1142 and 1200. And find out what the sign of the derivative is in these cases. Sorry, let me move that up. Find out what the sign of the derivative is in these cases, and then you'll find out whether it's a maximum, a local maximum, or a local minimum. If it's a local maximum, then you didn't find the lowest possible price. You actually found the most expensive it's going to be. But you can probably common sense tell that this is going to end up being the local minimum. 1142 is the correct answer. It's going to be the cheapest possible way to build it. So good. If you need to look at this, I know I went pretty quickly through this. If you want to look at it in good detail, it's on page 187, 188 in your textbook. You can have a peek at that and work through it. But I'm going to keep on moving because the next lesson is actually pretty hard. Okay. Extreme value problems in economics. And this is challenging because we're going to add a few new definitions. The actual questions aren't too bad. It's getting comfortable with the definitions, I think, is the hardest thing. And sometimes the numbers are a bit annoying in this section as well. But let's get into it. So this section uses skills we covered in the last section, maximizing and minimizing problem solving in economics. So we already have some of our things down. We know what a demand function is. We know what a cost function kind of is. We know marginal demand. We know marginal revenue. Or at least have a basic understanding of those concepts. Now we're going to build on that. We're going to have a few new definitions, and we're going to actually have two really nifty things that we have in red boxes. So first, the cost function is capital C of x, which is the cost to produce x number of items. We also covered the marginal cost, which is capital C prime of x, which is the rate of change of the cost with respect to x items sold. So now we have a new thing called the average cost function. So we can define the average cost as lowercase c. This is the average cost per unit when x units are produced. And we can define it as the average cost is equal to the total cost divided by the number of units, which makes sense. That's just average formula. If we wanted to minimize the average cost, we can do this by finding the critical points of this function. And there's actually going to be a short form for this. So you can actually do it two different ways. You can either get the average cost function, calculate the derivative, and calculate the critical points. And those are going to be your minimums when you find out if they're a minimum. Or we can actually do this. Using this definition, little c prime of x is going to equal, let's use your your rational derivative formula, which is, I think I've got it memorized now, low d high. It's usually low is q, so qp prime minus pq prime all over q squared. So in this case, it should be x times capital C prime of x minus C of x times just 1 all over x squared. So that's a way of looking at that. And if we're trying to find the minimum or the critical points, we're trying to set C prime, little c prime, sorry, to 0. So now we have this formula, and we can actually rearrange this formula to get a relationship between C and C prime. Do I have all these C's correct? Yeah. So rearranging this formula, we can actually, first let's do the derivative thing. Taking the denominator to both parts of it. So 0 is equal to C prime of x all over x, subtract C of x all over x squared. Maybe we didn't want to actually do that. Maybe we wanted to move the x to the other side. Oh, yeah. Sorry, I did that wrong. We want to multiply it to the other side. That's obviously what we want to do. So we multiply both sides by x squared, and it actually disappears. 0 times x squared is just 0. So we end up with 0 equals x, C prime of x minus C of x. And then we add the C of x. So C of x is equal to x C prime of x. Now this isn't too bad, but we can actually go one step further. We want to divide by x because then we're going to end up with our original average cost function on this side. So C of x all over x is equal to C prime of x. And long story short, we end up with this formula. If you're trying to, when you're trying to find when the average cost is a minimum, you don't actually have to calculate the derivative and find the critical points. You could do this instead. You could jump right to this last formula. You want to find out when the marginal cost, so capital C prime of x, is equal to the average cost, capital C of x divided by x. So you can actually jump right to this formula, and you've already kind of skipped the line a bit. Okay, so let's see how this formula works. First question, the cost in dollars of producing X number of 5 kilogram bags of flour is the following. So we have our cost function, capital C. Find the average cost and the marginal cost of producing 100,000 bags. So the average cost is just take that formula, divide it by X. Okay. And then this is actually just a straight up calculator problem. So when is it, make sure I've got this. Great. What is that average cost when it's 100,000? And I think it is $1.93. Kind of trusting this other work here. You could throw that all in your calculator, but it's just a calculator question. Just replace X with 100,000. Now, what is the marginal cost of producing 100,000 units? So that is our capital C prime. So you have to take this function, find the derivative. So derivative of this guy is bring down the 2. And derivative of this guy is just drop the x. And this guy disappears. And now find that value when C is 100,000. And that should be 0.63. So nothing really new there. It's just getting familiar that these are two different questions and kind of how they look like. And now let's get to the more interesting part. At what level will the average cost be smallest? And what is this average cost? So we're trying to find when little c, the average cost is the smallest. So we're looking for when little c is a minimum, so we're looking for little c prime's critical points. Now you could calculate little c prime again, you could use the formula and do this thing, but we're going to actually jump right to that red box formula that we have, which is c of x is a min when c of x is equal to c capital C prime of x. That's it. When average equals marginal. Just double check. When marginal is equal to average. Yep. When little c equals capital C prime. So let's write those formulas. In this case, we're going to actually solve this one. Yeah, right here. So the average one is 0.000001 x squared plus 0.43 x plus 140,000 all over x. And when is that going to be equal to the derivative, which is 0.000002 x plus 0.43. Sorry. So leave lots of space, write nice and big. This actually doesn't take a lot of lines to solve. So first thing we're going to do is bring the x up. So that's going to turn this term into an x squared. It's going to turn this term into a 0.43x. And that actually makes these two terms cancel out. And then we're going to subtract by the 0.02, and we end up with this on the next line. So after we subtract, this one is twice as big, so it leaves a negative 0.000001 x squared plus the 140,000, and the middle term is gone now. And then we just have to solve this for x. So subtract 140,000, divide by 0.000001, and then square root plus and minus. And you will get x is equal to plus or minus 374,165. And obviously the x is going to be an extraneous one, so we're looking for positive 374,165. And then that is when it's going to be the smallest. And now we need to find out what the cost is going to be at that time. So we need to sub in, we want to know what the average cost is at that time. So we want to know what little c of 374,165 is. And this is again a calculator question just like the last one. And it's not too hard to throw into your calculator. Try it on your own and it should get to $1.18 per bag. So that's how we can use that. That's our first one little special formula. And now we're going to get a whole bunch more definitions, so things are going to start getting a little bit confusing. So recall. The demand function, P of x, little p of x, is the price per unit that a company can charge if it sells x number of units. The revenue function, capital R of x, is equal to, so revenue is the money made in total. Revenue is equal to the number of units sold times how much you were selling them for. So basically P of x is how much you're selling them for. Think of it that way. And marginal revenue, just like in the other one, is its derivative, R prime of x. I don't know, I think we talked about profit last time. Profit is obtained by subtracting cost from revenue. So profit is you take your entire revenue and take away your entire cost from your last one. So we have a lot of different definitions now. If we want to maximize profit, we're going to end up with another thing. So profit is that. If we want to maximize profit, we're going to take P prime of X, which is actually just really easy. It's going to end up being R prime of X minus C prime of X. And then, of course, we're going to set this equal to 0. And so we end up with a really easy formula. Profit is maximized when R prime of X is equal to C prime of X. So all we got to do is add the C prime to the other side. And we end up with that. So here's our second really, really nifty formula. If you want to maximize profit, all you have to do, you can do two things. You could actually calculate the derivatives and find the critical points. Or alternatively, you can find when the marginal revenue is equal to the marginal cost. And this might be more useful because you might already have some of these things solved for individually. So a lot of different definitions. Let's actually go over some of the definitions, make sure we understand them all. If I have where I wrote them all down somewhere. Where did I write all these things down? It's not there. It's not there. So I write it on the next page. No. Oh well, we'll just do it from scratch. Basically, there's kind of two different columns we want to talk about. One is for sales, and one is for cost. So for sales, first we have the demand, which is sale price, kind of, which is our little p of X. Then, of course, we could do marginal of any of these things. I don't think we did marginal demand. We did marginal revenue and marginal cost. We never really did marginal demand. Now, revenue is XPX. And we call that R of X. So R of X is equal to X times P of X, and that's how we get to our total revenue. And then we can have marginal revenue, which is R prime of X. In terms of cost, so we have our cost function, which is C of X. We have our marginal cost, which is capital C prime of X. And now we also have our average cost, which is little c of X. And we kind of have when we can solve for average cost at a minimum, which is when little c equals c prime and stuff like that. So these are all of our definitions so far, and then there's one extra one. Profit is the thing that merges them together. So way down here, if you want to find profit, you have to take your total revenue and subtract total cost. So a whole bunch of different definitions. Hopefully you can keep them straight in your head. It might take some practice. Okay, let's keep going. Okay, in examples 2 and 3 in section 3.4, we talked about an example where we had Howard's Hamburgers and he had a yearly demand function. Demand function was 800,000 minus X all over 200,000. The cost function for this is capital C of X is 125,000 plus 0.42X. What level of sales will maximize profit? So maximize profit, we remember profit is equal to revenue minus cost. We don't have revenue yet, but we can replace revenue with X times our demand function minus cost again, right? Now we want to find the maximum profit. So you could do two things. You can either calculate the derivative of this, or we can use our new special rule. Our new special rule is max profit when r prime of x is equal to c prime of x, when the marginal revenue is equal to the marginal cost. That's it. So let's find what the revenue function is. So we want to do x times the demand, 800,000 minus x all over 200,000 is equal to, we need to do the derivative of this, technically, if we're trying to do the math right. Derivative of that has to be equal to the derivative of this guy, 125,000 plus 0.42x. So when those two derivatives are equal, then we should have our maximum profit. Now the right side is actually very, very easy. Derivative of this is just 0.42. Everything else just kind of gets dropped. This guy we want to simplify first, would make things nicer. So let's bring the x inside to turn it kind of into a polynomial. And actually we can pull the 200,000 to the outside to make it a easier looking polynomial. We don't have to deal with that in the front. So we're going to find the derivative of 1 over 200,000 times negative x squared plus 800,000 x. And the reason this is so easy to do the derivative of is the coefficients don't matter for derivatives. You can check with the product rule if you like, but this won't actually affect it. So it's actually just the derivative of this inside part. So the derivative of this inside part is going to be, well, the coefficient does stay at the front. It just doesn't create any more complications, any more ripples. This is going to be negative 2x plus 800,000. Okay, now we just need to solve that equation. And it's actually not too hard to solve. You can move the 200,000 up, and then subtract, and then divide. And you should get a solution of x is equal to 358,000. Let me actually just double check that real quick. $358,000. Yep. So therefore, there will be a maximum profit when 358,000 burgers are sold. So there's kind of a sweet spot for them. If they go beyond that, then I guess they're becoming less efficient or something. Or they're saturating their market too much and they have to sell it for cheaper. Something like that. Really, we're not immediately sure that this is actually the maximum. This could be a maximum or a minimum. But there's only one critical point. Because it's finance, there is actually only one critical point. And you can kind of intuitively guess it's going to be a maximum. You can just know it's going to be a maximum because the other extreme values are when they sell no burgers at all, or when they are selling the burgers for $0. Those will be the other two. Those will be the ends of our domain. And in both those cases, they're not going to be a better profit. They're going to be no profit at all. So there's only one critical point, and it's going to end up having to be the maximum. It's certainly not going to be a minimum. It's not going to go up from there. Yeah, so that's it for that one. Okay, now the hardest question. So, a store has been selling 200 compact disc players a week at $350 each. A market survey indicates that for each $10 rebate offered to the buyers, the number of sets sold will increase by $20 per week. So this actually sounds like a question that we did in the last section, and it is just like a question that we did in the last section. And we have the way of solving it that we did there, and that will actually work just fine. I checked it. There's it's not answering the questions that they set out here, but you will find the ultimate answer. You'll find the answer to be just fine. So what we kind of did is we talked about you start by selling 200 of them, and then X is the number of $10 rebates, and you'll go up by 20 of them. So plus 20 times your X. You start at $350 each, and you lose 10 times your X. And you want to find when that's a maximum value. So you could kind of set up that function, and you could solve it, and you will actually find the answers to B just fine. But it won't answer A the right way. So we actually have to kind of do this a little bit differently now to be able to answer it in a more economic sense. So find the demand function and the revenue function. This is neither. This function is really only good for one thing, and that's for finding that X value, which is going to maximize your profit. It's not really good for any of these other things, so we want to be able to actually set up functions. And the thing that makes this especially difficult is we can't define X the way we would want to define X in other situations. So we're actually going to say, let X be the number of CD players sold. Because it has to be. In all of our demand function and revenue function, in all of our functions in economics, X, our variable, is number of units sold. That's always the way they define it. So we can't actually define it this way, which actually makes the question a bit easier, I think. We have to stick with it in the economic sense. So we need to come up with an equation now, given X is the number of CDs sold. And what we're going to do is we're going to create the demand function. This is going to be a little bit weird. I'm not actually used to this. This is kind of new to me. I was just relearning this before the lesson. The demand function, what you want to center it around is the amount of, you have the original values, the 200 being sold at $350 each. We're going to create the demand function based on how much it's going to increase from those numbers. So we're actually going to say the amount that you're selling it for. Remember, P represents how much you're actually selling it for. So it's actually going to start at $350, we're going to say. So it starts with this kind of baseline, and then for every amount that we sell more than that, we're actually going to subtract. Let me make sure I read this again correctly. Yeah, so that's our baseline, and then we need to add to it how much extra units we're going to sell and how much we're going to sell them for. So the amount of new units that we sell is going to be amount of units sold, take away 200. It's a bit confusing. So that represents the increase in sales. So 350 was how much you were selling them for right at the beginning. Now you take the amount that you actually sold and you subtract the 200 you were selling for at the beginning. So this is how many new units you're selling. And now the decrease in price, so we're actually finding out how much the price is going to be adjusted by. So based on how many new units sell, we're actually going to decrease our price by $10 every time we have a sale. No, every time we have 20 sales. So you could basically divide this by 20. And they wrote it over there, but I think it makes more sense down here. So you take the number of increases in sales, you divide it by 20, and that's how much you have to lower your price by. So it's very similar to, it has a lot of the same characteristics as this, it's just a new way of looking at it. So now it's all just in terms of sale price relative to number of units sold. Hopefully that makes sense. It's confusing to me too, but you'll have more questions in the homework to practice it. So to tidy this up a little bit, this is like 1020, so this is like a half. 350 minus 1/2 of x minus 200. And to tidy up a bit further, you will end up with 450 minus 1/2 of x. Which means if you don't sell any units, you actually start with a price of $450. And then you lower it by 50 cents every single unit that you sell. So depending on how much units you want to sell, that's what price you have to set it at, is what we're saying there. Okay, so that's not too bad. Now what are we actually looking for? That's the demand function. What's the revenue function? So revenue is equal to x times demand. 450 minus 1/2 x, which is equal to negative 1/2 x squared plus 450x. Good. That's the hardest part of this question. It's just a new way of trying to solve this. It's hard when you already know one good way to solve this to actually try and learn another way. But this is the better way because it uses all the right definitions for economics, like I said before. Okay, how large of a rebate should the store offer to maximize its revenue? We want to maximize revenue, so we want to find when r prime is equal to 0. So first let's find r prime. And that should be, the 2 comes down, so it's actually negative x squared plus 450. That's not too bad. Oh, I don't know why I keep on to write 400. Plus 450. We'll set that equal to 0. Subtract 450. And square root. Oh, wait. Sorry, there's no x. There's no squared. Hopefully you caught that. The 2 comes down, so the half disappears, but there's no x. It's just negative x. 2, 2, 2. 2, 2, 2. So x equals 450 in this case. So the maximum revenue could be when the number of units sold is 450. Or it could be at any of the extremes. So there is kind of domain in this one. So it could be when you sell no units at all, or it could be when you sell the units for $0. So when P of X ends up becoming 0 or something, that'll be the far restriction on the other side. It is theoretically possible for it to be one of those other values if you were a really inefficient company, say, and you were constantly losing money. There are actually models out there where the more units a company sells, the more money they just lose because they're not selling the product for enough money. So actually the most money they can make is if they don't sell a thing, if they just close up shop right away. So that is theoretically possible. That's not going to be the case in this one, but you could check it really quickly if you wanted. Why don't we actually check this one nice and quick? So let's say 0 to 450, and let's say 450 to infinity or whatever. So we'll pick some number in here and check what r prime is. Why don't I just pick 100? So negative 100 plus 450 is positive. Maximize revenue. Sorry, I have to go into the revenue function, don't I? No, we want to know when R prime is going up and when it's going down. So when I sub in a small number, it's positive, and when I sub in a big number, it's going to end up being negative. So positive to negative is a max. Yeah. So nice and easy to check. Just sub the numbers in, and you found a max. Now, this wasn't our actual answer. This means that you need to sell 450 units. So you now need to actually find what the rebate should actually be. So you could sub that into a couple different ways to do that. Actually, you should probably pause this and try and problem solve how you're going to get to that part of the answer first. Okay, what I would do is I would sub it into the demand formula. So P of 450 is equal to 450 minus 1/2 of 450, which is equal to 225. So using that, it means you want to sell them for $225. So again, we've got two really good and important pieces of information, but we haven't answered the question. We want to sell 450 units. We want to sell them for $225. The question is how large the rebate should be. Well, we started at 350. So 350 minus our 225 equals, we should be rebating them $125. So therefore, we should offer $125 rebate. Okay, long lesson. Hopefully you can finish this lesson in class or for homework if it goes a bit too long. And then I'll give you all of tomorrow's class to work on homework for these 2 units. And we can maybe try another question like this to come up with this formula because that is a bit challenging and I'm likely to put something like that on the test. Okay, good luck.